So now let's talk about the concavity test. Let's say that I wanted to determine the concavity of a function over a specific interval, but I either didn't have a graph or I didn't want to graph it, and I'm wondering, what's the concavity of this function look like? So there is a test that we can do called the concavity test, and we're going to let f be a function whose first and second derivatives exist at all points in the open interval AB. Okay, so the derivatives have to exist, otherwise this concavity test is not going to work because it's based on the second derivative. And so here's what the test says. 1, if f double prime of x is greater than 0 for all x in that open interval AB, then f is concave upward on AB. 2, if f double prime of x is less than 0 for all x in AB, then f is concave downward on AB. So it's a very similar idea to what we were doing with the first derivative to find where functions were increasing and where they were decreasing, what intervals are they increasing and decreasing over. This is very similar, except it's for concavity. So looking at the cup shape, not whether the function is increasing or decreasing, but which way is it cupped, right? Is it cupped downward or cupped upward? So let's take a look at an example. Again, we're going to do one without graphing just to see what that looks like. I'm trying to find a good example here because I'm really bad at picking examples off the top of my head. Okay, let's say that we wanted to look at we want to find the largest open intervals whoops, where the function is concave upward or concave downward. And we also want to find any points of inflection. Okay, and then the function that we have is f of x is equal to 2 over x minus 4. Okay, so we're finding these intervals where the function is concave up or concave down, and then we're finding points of inflection. To do this, we're going to need to find the second derivative, right? That's our first step here. Find the second derivative. Well, to find the second derivative, we have to find the first derivative, okay? So, first derivative, I'm actually going to rewrite this a little bit, this original function that we were starting with. Rather than 2 over x minus 4, I'm going to write it as 2 times x minus 4 to the negative 1, just because that's actually going to make it a little bit easier for us to find the derivatives in that form. So to find my first derivative, negative 1 is going to come down front and multiply. That gives us negative 2. X minus 4, subtract 1 from the exponent. And then we would need to chain out the derivative of the inside, but you'll notice the derivative of the inside is just 1. So our first derivative of f is negative 2 times the quantity x minus 4 to the negative 2. Now we go to our second derivative. Same idea. Negative 2 is going to come down front and multiply. So that coefficient out front now is a positive 4. X minus 4 inside the quantity. Subtract 1 from the exponent, negative 3. Again, chain out the derivative of the inside function, but it's just a 1. Okay, so there is our second derivative function. Now, according to the concavity test, where the second derivative is greater than 0, that's where the function is concave up. And where the second derivative is less than 0, that's where the function is concave down. So those are the things that we're going to want to determine. Sometimes at this point, it can be handy to put the function back into the same form as the original. If you want to do that, it would look like this: 4 over the quantity x minus 4 cubed. It's the same function, just 2 different formats. So, how can we find where this thing is positive and where it's negative? Let's take a look at that. So if I have 4 over, was it x minus 4 cubed? Did I get that right? 4 over x minus, yeah, okay. If I want to know where is this greater than 0 versus where is it less than 0? Whoops, man, my stylus is getting very old and it's not working particularly nicely. Okay, there we go. So here are the two things that we want to look at, because that's going to tell us where we have our concave up and concave down. Because the function on our left-hand side is a fraction, and because the number that's in the numerator is positive, as long as the number that's in the denominator is also positive, the function's going to be greater than 0. So essentially, this expression here works out to be the same as x minus 4 quantity cubed has to be greater than 0. Similarly, the one where we're looking for it to be concave down, where is it less than 0? Numerator is positive. This is going to come out to be less than 0 when the denominator is negative. So when, x minus 4 quantity cubed is less than 0. Okay. And you can do a number of things to solve these. You can use algebra, you can, some of them you'll just be able to kind of look at and tell. Here, notice if we were to put in a value of 4 and cube it, this would come out to 0. Anything that we put in that's bigger than 4 and cube is going to give us a value that's bigger than 0. So basically, x has to be bigger than 4. Not equal to 4, because that's going to give us 0, but bigger than 4. If we put in a number here for x that's less than 4, that's going to give us a negative number inside the parentheses. And when we cube negatives, they stay negative. So any x's that are less than 4 are going to give us second derivative that's less than 0. So we'd be looking at concave down. So summarizing all of this, our function is concave up on the interval from, oh wait, let's see, 4. Yeah, okay, great, good. So we are concave up from negative infinity up to, but not including the value of 4. Again, open interval here. Our function is concave down from 4 to infinity, open interval. And then the point of inflection, that happens when the function changes concavity, when it changes from concave up to concave down. And so for this particular function, that happens when x is equal to 4.